The glass was cold. For 3,000 nights, the mountain peak remained silent, wrapped in the thin, freezing air of the Chilean Andes. Then a single digital sensor flared to life. It captured an arrangement of light that violated the foundational equations of modern astrophysics. The data arrived not as a gradual curve, but as a sharp, blinding spike that fractured the existing models of cosmic evolution. Computers at the operations base flagged the file automatically, isolating it from the routine telemetry streams. It was an impossible geometry, a structure spanning a sector of space that should have been completely empty, dark, and devoid of matter. This is the real story of the Vera C. Rubin Observatory's first anomalous discovery. On January 14, 2026, the data transmission reached the National Science Foundation's NOAR Lab computing hub in Tucson, Arizona. The source was the Simone Survey Telescope, located at an elevation of 2,663 meters on Cerro Pachon. This facility houses the Legacy Survey of Space and Time, an ambitious project designed to map the southern sky every few nights using the largest digital camera ever constructed for astronomy. The instrument features a 3,200 megapixel focal plane cooled to a staggering minus 100 degrees Celsius to eliminate thermal noise. When the automated calibration software processed image block 884 Delta, the system encountered an unresolvable error. The pixel array indicated a massive localized concentration of mass in a region where previous deep sky surveys, including the Sloan Digital Sky Survey and the European Space Agency's Gaia satellite, had recorded absolute nothingness. The implications of this reading were immediate and severe. It was not a glitch. It was a physical entity, a colossal structure measuring 4.2 billion light-years across. To understand the sheer scale of this anomaly, one must examine the fundamental rule of cosmology known as the cosmological principle. This principle dictates that when viewed on a sufficiently large scale, the universe is both homogeneous and isotropic. It means that matter should be distributed smoothly and evenly across the fabric of space. No single structure, cluster, or void should ever exceed a theoretical limit of roughly 1.2 billion light-years in diameter. Beyond that threshold, the gravitational forces of the early universe simply would not have had enough time since the Big Bang to pull matter together into a unified shape. Yet the data from Cerro Pachon revealed a continuous, unbroken filament of galaxies and dark matter that shattered this limit by a factor of 3. By January 22, 2026, an extraordinary session of the survey's core data team convened via an encrypted network. Dr. Marcus Vance, a senior astrophysicist specializing in large-scale structure formation, spearheaded the initial validation effort. The team scrutinized the raw data for potential optical artifacts, sensor bleeding, or atmospheric distortion peculiar to the Chilean sky. They found nothing out of order. The instrumentation had functioned flawlessly. The engineering logs confirmed that the telescope's 8.4-meter primary mirror had achieved perfect thermal equilibrium with the surrounding mountain air during the entire 3-hour exposure window. The anomaly occupied a sector within the constellation Hydra. It sat at a redshift of 1.4. This meant the light had traveled for 9.2 billion years to reach the mountain peak. The team began tracing the chronological history of this specific patch of sky to see if any hints had been overlooked by previous generations of astronomers. In October 2013, a team utilizing the Anglo-Australian telescope had noted a minor, statistically insignificant clustering of quasars in that general direction. At the time, the finding was dismissed as a random alignment, a cosmic coincidence of no physical importance. Then, in May 2021, data from the Dark Energy Spectroscopic instrument hinted at an unexpected gravitational tug affecting the velocities of distant background galaxies. But without the immense light-gathering power and unprecedented field of view of the Rubin Observatory's unique 3-mirror optical design, the true nature of the structure remained entirely hidden from human eyes. The newly acquired data stacked fact upon undeniable fact. The Rubin camera utilizes a mosaic of 189 individual charge-coupled device sensors, each engineered to a tolerance of mere microns. The anomalous structure appeared across 12 separate sensors simultaneously, ruling out any localized pixel defect or cosmic ray strike on the detector. Furthermore, the photometric redshift measurements indicated that the thousands of galaxies comprising this massive filament were all moving together, locked in a coherent gravitational dance that defied conventional timelines of cosmic growth. As February 2026 progressed, the research group expanded its inquiry to include independent verification methods. They requested archival data from the space-based Euclid mission, launched by the European Space Agency to map the dark universe. When the Euclid team cross-referenced their high-resolution infrared maps with the precise coordinates provided by the Rubin Observatory, the anomaly appeared once more. The independent dataset confirmed the existence of an immense, elongated overdensity of matter stretching across the ancient universe. This validation brought forth intense debate within the scientific community. Dr. Elena Rostova, a theoretical cosmologist known for her radical work on early universe phase transitions, proposed an unsettling hypothesis. She argued that this structure was not a mere collection of galaxies that had drifted together over time. Instead, she posited that it was the physical imprint of a cosmic string, a hypothetical topographically trapped defect in the fabric of space-time itself, formed during the first fraction of a second after the Big Bang. If Rostova's theory held true, the filament was not an accident of gravity, it was a scar. A microscopic tear in reality that had expanded to cosmic proportions. Such a defect would possess an almost unimaginable linear density. A single kilometer of a cosmic string would weigh as much as the entire Earth. As it moved through the early universe, its immense gravitational wake would act as a cosmic snowplow, rapidly drawing vast quantities of gas, dust, and dark matter into a massive, elongated wall, long before standard gravitational collapse could even begin. This mechanism neatly explained how a structure of such immense scale could exist so early in cosmic history, but it did so at a catastrophic cost to the established framework of physics. Mainstream cosmologists immediately pushed back against this provocative interpretation. Dr. Arthur Pendleton, an authority on cosmic microwave background radiation at Princeton University, led the counter-argument. He cautioned that introducing hypothetical constructs like cosmic strings to explain a single anomalous observation was a dangerous departure from rigorous scientific methodology. Pendleton maintained that while the Rubin Observatory's data was undoubtedly revolutionary, it did not require the abandonment of the cosmological principle or the standard model of cosmology. Instead, Pendleton suggested a more grounded explanation. He proposed that the apparent 4.2 billion light-year structure was an optical illusion created by cosmic lensing on an unprecedented scale. He argued that an intervening, hitherto undetected concentration of dark matter closer to Earth was bending and distorting the light from much smaller, disconnected galaxy clusters in the far background. This gravitational distortion could warp the background light, smoothing it out and making separate groups of galaxies appear as one continuous hypermassive structure. To resolve this intense conflict between the radical and mainstream interpretations, researchers required even more precise data. They turned their attention back to the Rubin Observatory's ongoing survey operations. The true power of the facility lies not just in its massive camera, but in its ability to return to the same patch of sky night after night, accumulating data over a full decade to detect minute changes and ultra-faint details that no other instrument can perceive. By April 2026, the observatory had completed its fourth comprehensive pass over the Hydra sector. The new images provided a significantly higher signal-to-noise ratio. The data revealed that the galaxies within the anomalous structure were not merely aligned in space. They exhibited a distinct synchronized polarization in their orientations. This specific physical characteristic strongly undermined Pendleton's gravitational lensing hypothesis, as standard intervening dark matter lenses do not induce such uniform intrinsic polarization across independent background galaxies. The evidence was tilting back towards something genuinely anomalous. The community faced a profound dilemma. Either the universe is fundamentally non-uniform on large scales, or our understanding of gravity over vast distances is completely wrong. Every cosmological simulation ever run on the world's most powerful supercomputers assumed that matter would homogenize at scales above 1 billion light-years. These simulations form the baseline for how we calculate the age of the universe, the expansion rate of space, and the total budget of dark matter and dark energy. If the Rubin Observatory had found a real physical structure spanning over 4 billion light-years, those simulations were no longer valid representations of reality. The entire mathematical foundation used to describe the history of the cosmos would need to be dismantled and rebuilt from scratch. Meanwhile, independent teams began looking for corroborating evidence in the cosmic microwave background, the ancient afterglow of the Big Bang itself. If a structure of that magnitude existed 9.2 billion years ago, it must have left a corresponding imprint, a subtle cold or hot spot, in the radiation that has been traveling through space since the universe was just 38,000 years old. Researchers analyzing historical data from the Planck satellite discovered a faint, long-overlooked temperature fluctuation precisely aligned with the coordinates of the Rubin anomaly. The piece of the puzzle fit perfectly, yet it only deepened the underlying mystery. The discovery shifted from a localized astronomical curiosity into a full-scale crisis for modern astrophysics. The data suggested that the early universe was far more active, chaotic, and structurally complex than anyone had ever anticipated. It implied that the smooth, orderly cosmos described in standard textbooks is merely a localized illusion, a comfortable misconception born from our previously limited ability to see into the deepest, darkest corners of space. You need to understand that this is not a problem that can be solved by simply tweaking a few numbers in an equation. It demands a fundamental shift in how we perceive the universe. If matter can coalesce into such monstrous configurations, then the laws governing the distribution of mass in the cosmos are driven by forces or conditions that remain completely unknown to modern science. We are looking at a feature of reality that we do not have the vocabulary to describe. To fully dissect why this discovery has sent shockwaves through the global scientific community, we must trace the precise mechanical chain of events that occurred inside the observatory during those critical exposure hours. The Rubin Observatory does not operate like a standard telescope, where an astronomer sits at a console and points the lens at a single object for half the night. Instead, it operates as an automated factory of the night sky. The telescope moves with violent precision, slewing to a new patch of sky every 30 seconds, stabilizing its massive weight within milliseconds, and snapping two 15-second exposures before moving on. The entire sequence is governed by an advanced scheduling algorithm that balances atmospheric clarity, wind direction, and lunar interference. When the telescope slewed to fields within the Hydra constellation, the mechanical logs recorded perfect structural performance. The oil pads that support the 350-ton mount maintained a uniform pressure of 5 megapascals. The active optics system, which utilizes 72 pneumatic actuators behind the primary mirror to constantly correct the shape of the glass against the pulling force of gravity, adjusted its pressure values every 2 seconds. There was no mechanical shutter. There was no tracking error. The path of light entering the telescope was absolutely uncompromised. The light passed through the custom-engineered filters, each the size of a man's torso, designed to isolate specific wavelengths of radiation. For this specific observation, the telescope utilized the Z-band and Y-band filters, which are tuned to capture the deep red and near-infrared light emitted by the most distant objects in the known universe. Because space itself is expanding, light from ancient galaxies is stretched as it travels across billions of light-years. By the time it reaches Earth, visible light has been shifted down into the infrared spectrum. The Rubin camera was built specifically to capture this stretched, exhausted light with unprecedented fidelity. The data stream generated by these exposures bypassed the local mountain storage and was immediately routed down the steep slopes of Cerro Pachon via a dedicated high-speed fiber optic link. The signals traveled through the underground conduits to the city of La Serena, then darted across the ocean floor via submarine cables to the high-performance computing centers in North America. This data pipeline is engineered to process every single image within 60 seconds of the shutter closing, running automated pipelines that look for transient events such as exploding stars, moving asteroids, or sudden fluctuations in the brightness of distant quasars. When the pipeline encountered image block 884 delta, the system did not encounter a typical software failure. It encountered a statistical variance that broke the sorting parameters. The software is programmed to recognize known configurations of matter, classifying stars as point sources and galaxies as extended profiles. It then calculates the local density of these objects against a running baseline of the surrounding sky. In the Hydra sector, the baseline exploded. The algorithm flagged a concentration of distinct high redshift galaxies that was 10 times denser than the surrounding cosmic background. By February 12, 2026, the data had been manually processed by 3 independent data validation pipelines at different academic institutions. The first group, operating at the University of Washington, used an empirical model to estimate the distance to the galaxies based on their observed colors across 5 different filter bands. The second group, located at the Princeton Institute for Advanced Study, deployed a neural network trained on millions of simulated galaxy clusters to verify that the overdensity was a real, physically bound structure rather than a random projection of foreground and background objects. The third group, working directly from the operations center in Chile, analyzed the raw pixel telemetry to ensure that no light leaks or scattered reflections from bright nearby stars had contaminated the exposure. All 3 analysis paths converged on the exact same conclusion. The structure was real. The galaxies were grouped at the same precise evolutionary depth, meaning they all formed during the same historical epoch of the universe. The weight of the data was undeniable. The total mass of the filament was calculated at 10 to the 16th power of solar masses. This number represents the combined weight of 10,000 Milky Way galaxies packed into a single continuous structural thread. To place this measurement in a broader historical context, we must examine previous discoveries that have challenged our understanding of the cosmic layout. In 1989, astronomers Margaret Geller and John Huchra discovered the Great Wall, a sheet of galaxies measuring roughly 500 million light-years in length. At the time, its existence surprised the scientific community, but it still fell comfortably within the theoretical bounds of early universe physics. In 2013, researchers identified the Hercules Corona Borealis Great Wall, an immense superstructure estimated to be nearly 10 billion light-years across. However, that discovery relied entirely on the mapping of gamma-ray bursts, which are brief, distant explosions that provide an indirect and often controversial trace of where matter actually resides. Many cosmologists remained skeptical of its true scale, arguing that gamma-ray bursts do not necessarily map out a continuous, gravitationally linked entity. The Rubin Observatory's discovery was fundamentally different. It did not rely on indirect tracers or fleeting flashes of radiation. The 3200 megapixel camera had mapped the individual member galaxies themselves. It recorded the precise positions, shapes, and light profiles of thousands upon thousands of separate stellar systems, providing a direct, high-fidelity skeletal map of the matter distribution across that sector of space. This was not a tentative inference based on a few isolated data points. This was a direct structural measurement of an impossible reality. As the implications of the discovery rippled through academic departments worldwide, the focus shifted from data validation to theoretical reconciliation. How could something so immense form in a universe that was supposed to be smooth and predictable? The standard model of cosmology, known mathematically as lambda CDM, relies on the assumption that the early universe was incredibly uniform. The cosmic microwave background radiation shows that the density of matter in the early cosmos varied by only 1 part in 100,000. These tiny ancient ripples were the seeds that gravity slowly grew over billions of years into the stars, galaxies, and clusters we see today. But gravity is a slow, methodical force. It propagates at the speed of light. For matter to travel across billions of light years and organize into a unified, continuous filament requires more time than the universe has existed since the Big Bang. If the lambda CDM model is correct, the universe is 13.8 billion years old. At that age, a structure measuring 4.2 billion light-years across simply cannot have completed its formation process by a redshift of 1.4. There has not been enough time for the gravitational news to travel from one end of the structure to the other, let alone for the matter to move into place. This is where the theoretical framework begins to splinter. Dr. Elena Rostova's cosmic string hypothesis, which had initially been met with profound skepticism, began to receive a more detailed analysis from researchers looking for a way out of the mathematical dead end. Cosmic strings are remnants of a primordial era, theoretical lines of pure energy left behind when the universe underwent a rapid cooling phase just after cosmic inflation. Think of them like the cracks that form in a sheet of water as it freezes into ice. They are not made of matter, they are lines of undecayed vacuum energy trapped in the geometry of space. Because a cosmic string would possess an immense, almost infinite gravitational tension, its behavior in the early universe would completely bypass the slow, orderly laws of standard galaxy clustering. As the string wiggles and oscillates through space at near the speed of light, it leaves behind an intense gravitational wake that acts like a cosmic funnel. Matter from the surrounding primordial soup does not need to slowly attract itself over eons. Instead, it is violently compressed into the string's wake within a matter of millions of years. This rapid accumulation process could theoretically generate a colossal, continuous wall of galaxies early enough to match the precise timeline recorded by the Vera Rubin camera. However, the scientific community remained deeply divided over this explanation. Accepting the existence of cosmic strings would mean validating a concept that has evaded direct experimental detection for decades. It would require particle physicists to rewrite their models of high-energy interactions, introducing forces and fields that have never been observed inside the Large Hadron Collider or any other laboratory on Earth. For many conservative theorists, this was too high a price to pay for a single astronomical observation. They preferred to search for explanations within the boundaries of known physics, even if those explanations required extraordinary stretches of probability. Dr. Arthur Pendleton's alternative model of gravitational lensing underwent significant refinement throughout March and April of 2026. Lensing occurs when a massive foreground object, such as a cluster of dark matter, acts as a cosmic magnifying glass, bending the paths of light rays traveling from objects located far behind it. If the alignment is precise, this bending can distort the images of background galaxies, stretching them into arcs or duplicating their appearance across large patches of the sky. Pendleton argued that the Rubin camera was looking through a highly complex, multi-layered gravitational lens system that had completely distorted the true layout of the background universe. He suggested that there was no real 4.2 billion light-year filament. Instead, his models proposed that 3 or 4 completely separate, much smaller galaxy clusters, located at varying distances from Earth, happened to line up perfectly along our line of sight. The gravitational fields of the closer clusters warped the light from the more distant ones, smoothing out the gaps between them and creating the illusion of a single, continuous, hypermassive structure stretching across the sky. To test Pendleton's lens hypothesis, astronomers needed to measure the exact distance to every single individual galaxy within the suspected structure. Photometric redshifts, which use filters to estimate distances based on color, are highly efficient for mapping millions of objects quickly, but they carry an inherent margin of error. To get an absolute, undeniable measurement, researchers required spectroscopic data. This process involves capturing the light from a single galaxy, passing it through a high-precision prism to split it into a detailed rainbow spectrum, and measuring the exact displacement of known chemical elements such as hydrogen and oxygen lines. In May 2026, a request for emergency director's discretionary time was submitted to the operations board of the Gemini South Telescope, an 8.1-meter optical instrument located just a few kilometers away from the Rubin facility on an adjacent mountain peak. The Gemini telescope is equipped with a powerful multi-object spectrograph capable of isolating and analyzing the light from hundreds of faint galaxies simultaneously. The board recognized the critical importance of the Rubin discovery and granted the observation window immediately. Over 3 consecutive nights of exceptional atmospheric clarity, the Gemini South Telescope locked onto the precise coordinates of the Hydra anomaly. The spectrograph split the ancient light into its constituent wavelengths, tracing the unique chemical signatures of stars that lived and died 9 billion years ago. The data processing computers worked through the night, calculating the exact velocity and distance for every target galaxy in the field. The results from the spectroscopic analysis were definitive. The lensing hypothesis collapsed. The galaxies were not at different distances. 94% of the targeted systems sat at the exact same spectroscopic redshift of 1.4112. This confirmation eliminated any possibility of an optical illusion or a chance alignment of separate background structures.